This program will demonstrate the presence of antenna standing waves and the effects of polarization, ground plane, and director elements. It will be presented by Arthur Greenberg, a licensed radio operator since 1924 and a holder of an extra class amateur license and a commercial license. He will be assisted by Madeline Greenberg, a licensed operator since 1950 and holder of an advanced class license. This demonstration was conceived and developed by Arthur Greenberg. For review, the power developed by a radio transmitter is present at the output of that transmitter. To obtain maximum radiation, the transmitter must feed a resonant antenna. For an antenna to be resonant, its electrical length should appear to equal the wavelength of the radio signal or be a multiple of that wavelength, such as a half wave or a quarter wavelength. The radiated signal is polarized, as determined by the position of its electrical and magnetic lines of force. These are determined by the position of the antenna's radiating element. An antenna should either be horizontally polarized, the electrical lines of force running parallel to ground, or vertically polarized, the lines of force running perpendicular to ground.
We have here a dipole antenna connected with a coaxial cable to our transmitter. The transmitter has a power output of about 15 watts and its associated power supply, of course. In discussing the antenna system, we should point out that on the other side we have a receiving antenna. We'll do most of our concentrating on the transmitting area of the system, but we should give you some descriptions of a part of the items and what they're doing so that you have a better picture of what we're going to demonstrate. Here we have a dipole antenna that's being fed with the power from the transmitter, and I want you to see something very interesting. You know, you may have read in the books that you have standing waves on the antenna or on the transmission line, and it's almost impossible in reading these books to comprehend what they mean by standing waves of voltage and current. Well, we're going to try to show it to you in actuality. We have an aluminum bar here, and the aluminum bar is split at the center. There's a little insulator at the center so that we have a split dipole being fed with this coaxial line. It's a solid aluminum bar, but I want you to see something. We have standing waves of current. Now I have a little lamp. Now a lamp lights by virtue of current. When the filament inside that lamp senses current, the filament gets hot and emits a light. Now if you notice when I turn on the transmitter, this little light at the center is lit. Can you all see that? Now let's see something else. Now don't forget, this lamp is bridged across an inch or 2 inches of the aluminum itself. On ordinary thinking, that would be a short circuit. But when we're dealing with radio frequencies, there's a skin effect that takes place, and all of the current and all of the voltage is on the skin of this element. Not through the element, but on the skin of the element. And by putting this lamp just across the 2 inches of this aluminum at the current loop, I'm able to light that light. That being the case, and since we saw in the pictures in the books that these ends of the antenna are voltage loop, let's see what happens. I have here a fluorescent lamp. The fluorescent lamp contains a gas. When that gas is subjected to a voltage, it will ionize the gas, and then the fluorescent coating will give off a light. That being the case, we're going to put the lamp to the end of the antenna, and I want you to notice the fluorescent lamp lit. Now that's being lit by the voltage that's developed in the end of the antenna. If I put the same lamp toward the center of the antenna, it's not lit at all. Now don't forget, this is 1 bar of aluminum. The other end of the antenna has a voltage loop. By the same token, if we bring this toward the center, you don't have the voltage loop, you have the current loop. So that you have to be able to understand what they mean by standing waves, and this is a very, very vivid and visual demonstration of the standing waves of voltage and standing waves of current on this dipole antenna. Now when we examine the dipole antenna, I created a little pickup antenna which is nothing more than a dipole split in the center, and I have a little incandescent lamp connected to it. Now, when I bring this pickup antenna parallel to the broadcasting antenna, I want you to notice how that light lights up. Now, a dipole antenna has the characteristics of radiating on both sides of that dipole antenna, so that if I put my pickup antenna on this side, it lights up. By the same virtue, if I put it on this side, it will also light up. Now, on the sides of the antenna, there's no pickup. Another thing I want to point out to you is that this antenna is horizontally polarized. Now, what does that mean? That means if your receiving antenna is in a vertical mode, vertical position, the RF will not be picked up very well by the receiving antenna. This antenna is horizontally polarized. Now, the same effect will take place when I use this antenna in a pickup mode, because now when I turn this around in a plane opposing the receiving antenna, the signal falls off. If you remember, when I brought this antenna over to the side, there is no pickup. So the dipole antenna is broadcasting with two tremendous lobes on either side. And I hope that that's clear to you. I wanted to show you also, while I'm in the dipole area, absolutely the polarization of the antenna. If you remember on the dipole antenna, when it was horizontally polarized, I was able to demonstrate to you the polarization. Now, I have an antenna here that's a half-wave length long. It's 38 inches long, but I bent the ends down. I bent the ends down for a specific purpose. I wanted you to see that this antenna still has its voltage loops at the end, okay, and the current loop at the center, so that our electrical field is in the center where the current is, and the electrical field is the one that sends out the radio waves. Now, with this bent dipole, I want you to take a look at the polarization. Horizontally polarized. This should give you a very definite understanding that even though these ends are part of the antenna itself, and it's one bar of aluminum, that the current portion is the portion that's doing the radiating, and therefore when I have this in its plane, it radiates. In the horizontal plane, the voltage portion does not radiate. There is a little current being radiated. If I put this very close to it, I'm sure you'll see a little bit of light, because don't forget, as I pointed out to you before, the current is maximum at the center, falling off to zero at the ends. But there is a little bit of current here, so that there is some radiation from this bent portion, but a very minimal amount. But that's the way the radiation takes place within the current portion of the antenna, and it's very important that you understand that. Okay? Now we're going to go into the vertical antenna. And I have here a quarter-wave magnetic base antenna. Of course, this one has been secured for the use in our demonstration, so that this length of it, is applicable to the 146 megahertz that we're using as our transmit frequency. We have a little lamp connected across a portion of the current portion of the antenna, and let's see what happens when we turn the power on. I don't know whether you can see it or not, but the light is lit rather dimly, but it's lit. And I just want to point something out when it comes to this type of antenna. A quarter wavelength antenna of itself is not a resonant length antenna. In order for it to be a resonant length antenna and to accept the power and radiate it, the power that you have available in the car or whatever, this antenna has to look like a resonant antenna. And the resonant antenna means that it should have a ground plane effect. And in the case of your car, of course, you're putting it on the roof of your car, which is metal, and that creates the ground plane effect. Now, what we did was we brought along a cookie sheet, just an ordinary cookie sheet from Madeline's kitchen, and we're going to try it and see what happens when I put the same antenna onto a metal base. Now, before I try this, I'm going to burn this bulb out for sure. I'm going to put a high current bulb in the place of this. I only put that low current bulb in there so that you could see it in the situation where I had it without the base. Now, this should be a high current bulb. Let's see if I'm right. Oh, let's try it. Is it lit there? I don't know whether you can see the intensity of the lamp now as compared to what it was before. We'll switch it back and forth. We'll switch it back and forth. Can you see that all right? Okay. I'm going to switch it back. I'm going to take this metal plate off. Look at the brilliance. Okay, turn it off. I don't know whether you can see it lit or not. Probably not.
Very dim.
Very, very dim. Now watch what happens when I put this onto the metal pan. The antenna now is looking at resonance. This plate is filling in the other side of the quarter wave antenna as far as the transmission line is concerned, so that now the power from the transmission line is able to see its impedance and get the power into the antenna for radiation. I want to point out that in your vertical antenna, or like I told you in any antenna, the top of the antenna is always a voltage loop. The same thing, if I go back to the current loop, the same lamp will not light. Don't forget, this is a bar of metal, stainless steel metal. When I put this at the voltage portion of the antenna, the standing waves in here are such that we get the current loop at the bottom where we can light the incandescent lamp, and the top of the antenna is a voltage loop where we can light our fluorescent lamp. Well, Madeline wants me to show you how the pickup antenna of this antenna goes. Here's our pickup antenna in a vertical mode. Remember the other one was horizontal? In this case, our pickup antenna has to be in a vertical mode, vertical position, in order to pick up the RF. And the other one was just exactly the opposite. But here we have our antenna. This antenna is radiating. You remember the dipole had its radiation on two sides? This antenna is omnidirectional, and you get radiation all around the antenna, completely around the antenna. The antenna is radiating in the form of two loops. Not two loops, but a loop, like a donut with the RF coming off the sides of the antenna, 360 degrees around that antenna. Now, while we're in the vertical antenna, I'm going to go to a different type of vertical antenna. I simply have a vertical antenna here, and I'm going to put it into this receptacle, and I'm going to bring my coax line from the termination of the vertical antenna that I'm placing here. Okay? And I'm going to put this back onto our transmitter. And we'll examine the characteristics again of this vertical antenna. Oh, try it, man. No, it may be lit. Try it again. The light is not lighting. Let's see if it's getting any radiation at all. Try it. Yes, there is some radiation from it. Now, this is very interesting. That bulb is not lighting. I'm going to check. I'm going to do something here to demonstrate the difference in the quarter wave antenna when it looks at ground plane. The four radials, the four little wire radials. Try that again, dear. Nothing. All right. Turn it off. I have here 4 pieces of wire. These are going to be our ground plane. These are the same length as our quarter wave vertical antenna, and I'm simply going to clip them on to a portion of the base of the antenna at the termination of the antenna. Okay? Now all we did was clip on and create a ground plane effect. Now I want you to see something. The lamp that was lit so dimly before that you couldn't even see it lit now lights brightly, and now there's no question about pickup from the antenna. Can you see it? No question about the horizontal vertical plane of this antenna. And we're going to examine this antenna with a little care and see what we have here. Because here we have a situation where we're using a ground plane. where these four pieces of metal are quarter wavelength long in an opposite plane to the vertical itself. And these wires here are not looking at themselves as part of the antenna, but rather as part of the antenna system. They are acting as a reflective surface so that this quarter wave antenna is seeing its image by virtue of the ground plane wires, and this termination that we have from the coax line is now looking at a resonant antenna and being able to radiate the power, accept the power. Before, when I had these radials off, it would not accept the power. Now, we have to examine, well, let's see if we have our voltage loop. Oh yeah, there's our voltage loop, no question about it. And there's our current loop where the lamp is lit. Okay? Now, we want to examine this with a little care just to see what's doing here. If I were to take off 3 of these radials, okay? Now let's examine this now and see just what do we have. If you remember before, when we had the dipole antenna, we had a bar of aluminum, and each side was 18 or 19 inches long, quarter wave, so that the total length of the antenna was 38 inches in the resonant length. Well, now we have a strange phenomena. We actually have here a bent dipole. Here's your vertical, and here's your other part of the dipole. So that now you don't have a vertical type of antenna. The radiation from this antenna will not be the same as we had before when we had a true vertical antenna with our donut all around it. Here we have a distorted quarter wave antenna, not a distorted antenna, where the plane of each one of these legs is almost at 90 degrees angle to each other, so that you'll have cancellation, you'll have various things happen to it. What I'm trying to bring out is that if you're going to put radials on your antenna system, on your vertical, make sure that you put enough radials on, at least 3, so that the antenna is going to act as a vertical antenna. See, this here will have a voltage loop now, here, okay? And you'll have a vertical loop here, because we now have a dipole antenna. If I were to put back the radials and put the 4 radials back, I want you to particularly note also that everything here, I'll use the word haywire, was just put together from normal formulas in the book. Nothing was done here to create an effect. If I were going to do this in a professional based way, I'd have these radials nice and straight, and I'd have them uniform and tightened on really wonderfully. Now, I want you to see something. I have my power on now, and these are not radiating. Do you remember they don't have a voltage loop on them? If you recall before, when I had the one radial on, it was a dipole, therefore we had a voltage loop. But because we have 4 radials, and because the antenna itself is looking at these radials as a ground plane, not as a portion of the antenna, radiating portion of the antenna, but simply an image of the vertical itself, we now have a true quarter wave antenna that's radiating the same as the one I showed you on the car, the one on the mobile, where we have our donut all around this antenna and radiating out 360 degrees around it in a form of a low angle of radiation. Okay? I think that'll take care of the knowledge that we want to learn about vertical antennas. And we'll see if we can fill you in with some other information. We're now going to demonstrate a different type of vertical antenna. It's commonly known as a 5/8 wave vertical antenna, used in mobile installations or in fixed installations as well. You can see the antenna here. You notice it's quite a bit longer than the antenna that we demonstrated before, but it's cut for the same 146 megahertz. What we have here is a 5/8 physical length of the antenna. Now, actually, in reality, this is actually electrically 3/4 of a wavelength long. But this little coil in this base is picking up 1/8 wave of the resonance to create the resonance, okay? So now we have an antenna. I told you it's electrically mechanically 3/4 of a wavelength long. Being 3/4 of a wavelength long, I told you originally that the end of the antenna is a voltage loop. If the end is a voltage loop, then a half wave down from the end, we have another voltage loop. So that if I put the lamp up here, Okay, can you see the light lit? Now, if I bring the lamp down here, to this point here, you notice I also have another voltage loop. I will not have the voltage loop down here, shouldn't be anyway, down here, because this is the current loop. Now, as I pointed out before, the radiation characteristics are such that the current loop is the portion that's sending out, has the electrical field is sending out the radio waves. So that at this point here, we'd have our radiation, and we'll also have radiation from the electrical field that's developed in this portion of the antenna. And what happens is both radio waves meld together, and they'll find that this type of antenna has a little bit added gain because each one of these radiated electrical fields or radio wave fields is reinforcing each other. So that the 5/8 wave antenna is a very interesting and very effective vertical antenna for the purpose. Now we're going to create what is known as a yagi or beam antenna. We have our dipole antenna, just the ordinary dipole antenna. Now we're going to put elements. So we have a wooden boom here, and we're going to have elements here. Now this is a reflector, which is 5% longer than our driven element, okay? Now we have two directors. This is the director 1, which is about 5% away from the driven element, and I have a director number 2 here. Now these are not connected in any way with our driven element, with our dipole driven element. And yet, I want you to notice the reaction of this antenna. I don't know whether you can see how bright this lamp is. You remember with the dipole before, I had to have it quite close to the antenna to get it to light up? I want you to look at this, and I want you to look at the polarization. Okay? Horizontally polarized. And you'll find that on this antenna, the signal will fall off on the sides. See it? Very sharp. You have to leave that on, please. Can you see it? So we have a very forward loop. Now I want you to notice something particular on this antenna. I'm at the back of the antenna, right? And the transmitter is on. You can see the little incandescent lamp lit. And I want you to notice that there's absolutely no pickup. Well, there is some pickup, not enough to light the light. But I want you to see the front to back ratio of this beam antenna. The reflector is 5% longer than the driven element. What happens is the radio frequency waves are building up and collapsing on this element at 146 million times per second. When you put a longer element here, it takes a little bit longer time for the RF to bounce back and forth on the element. Difficult to comprehend, but understand it. As soon as we put a reflector behind that driven element that's 5% longer and spaced a reasonable amount behind it, it forces the signal to go in that forward direction. By the same token, the directors, being 5% shorter, will take less time for the RF to build up on them, and it causes a reaction, a phased effect that forces the signal into that forward direction. The beam antenna or yagi antenna is extremely effective, and the gain from it, as you can see, is simply tremendous. It gives you a good idea of the difference from just any old kind of an antenna to an antenna that has been designed for an effect. Now, another thing I want to show you, these elements are not connected to the driven element, but I want to show you something. We know we have a voltage loop on the antenna, but you also have voltage loops on the parasitic elements, just as well as you have on the driven element. In other words, there are standing waves of voltage and current on the parasitic elements, which are coupled to the driven element, and that's what's causing that signal to be forced into that forward direction. And I hope that you can understand it. I hope it's vivid enough for you to understand.
You didn't say it was a wooden bowl?
Yes, I did. Okay, we're now going to demonstrate a quad antenna. A quad antenna gives the same characteristics as the beam antenna that we showed you before. We have a quad antenna. It's fed at the base here with this coax line from the transmitter. And a quad is a full wavelength long in element length. Being full wavelength long now, we can discuss it in two ways. We can either say this is a full wavelength, or we can consider it as two half wavelengths. Now we're going to discuss it as two half wavelengths for a very obvious reason. If you notice, we have a current loop at this top portion, and we have a current loop at this bottom portion. The bottom portion, of course, is the portion right by the termination. Now, this is the portion that's doing the radiating of the electrical field and the radio waves. Since we have two radiating areas, they're both radiating and they're both tending to reinforce each other, so that this antenna has a little bit more gain than a two-element yagi. As a matter of fact, this antenna would be about the equivalent of a three-element yagi in actual effectiveness at the receiving end. I want you to notice that the antenna has a voltage loop on the side, okay? And of course, there'd be no voltage loop here. That's the current loop. And it's the same situation that we had before when we demonstrated the standing waves on the dipole or on the yagi or whatever. So that's a very effective antenna. I want to also show you the directional characteristics of the antenna. We have here my pickup antenna. I don't know whether you can see the light on the pickup antenna or not. If I just turn this just a little bit, the light goes out. You see it? It's a very sharp lobe in the forward direction, and there'll be very little pickup from the back of the antenna. The quad does not have quite as much front-to-back ratio as the yagi, but in the forward direction, it's extremely effective. And even though the wire is in the form of a square, don't forget it's horizontally polarized because that's where the current loop is. We bring this into the vertical plane, no light. In the horizontal plane, plenty of radiation. So that it's a very effective antenna and a very good antenna. So much for the quad. The delta loop is an effective antenna. It's basically a full wave loop. And we have the same situation that we had before on the quad loop, where we have a current loop at the top and a current loop at the bottom. The antenna is basically horizontally polarized, okay, and effective, of course, on both sides. It was developed primarily because it's easy to support, particularly on the lower frequencies where we're dealing with 4 megahertz or 7 megahertz, where you have antennas that are in the 120-foot range or in the 66-foot range, where this could be strung between two trees or two supports. And it's a very effective antenna and a good antenna. And we thought that in view of the demonstration, we should put this into the comparisons between antennas. So much for the delta loop.